My name is Miriam Andrew. My matrix number is CD240084. I will present about introduction, literature review, and problem definition. Statistics is a branch of mathematics with an engineering focus that explains how machine, material, and structure maintain balance utilizing Newton's law of motion. Its primary deals with force that cause object to move or material to bend and break. Static equilibrium refers to system where objects remain stationary or move at a constant speed in contrast to dynamic, which study accelerated motion. Static is essential in engineering for understanding and designing systems meant to remain steady. A rigid body is in equilibrium when all the force and torque acting on it add up to zero. This means the object doesn't move or rotate. To analyze such system, we create a simple model of the object. Draw the diagram showing all the force acting on it and then use equation to find any unknown force or moment. A common example is a ladder leaning against a wall, which forms a triangle with the ground and wall. Force on the ladder include its weight, let the ground upward, a support, and friction at the wall and ground. This example is often used to explain balance, friction, and basic trigonometry, making it a simple and clear way to understand how statics work. A key concept includes resultant force and moment must be zero. For an object to be in equilibrium, all forces acting on it must cancel each other out, and the total torque or moment must be zero. This ensures that the object does not move or rotate. Second, equilibrium includes both rotational and translational states. A rigid body in equilibrium remains stationary or move at the constant speed without rotation, indicating balance in both linear and angular force. A rigid body achieves equilibrium when the total force and total moment acting on it are zero. This means the body remains stationary or move at a constant velocity. Below are the practical examples of equilibrium in rigid body. First, ladder leaning against a wall. Temporary scaffolding used in construction and repair rely on ladders for access. Static help engineers calculate force such as the friction between the ladder and wall, the maximum load of the scaffolding can hold, and the ideal ladder angle to ensure the safety and stability. Second, bridge support by cable or beam. Substation bridge are where decks are suspended by cable over tower. Rely on static to analyze force acting on the bridge and cable. Engineers use this calculation to determine the maximum load, tension in cable, and bending moment in beam. Ensure secure and efficient design. Third, crane lifting on heavy object. Crane essential for high-rise construction. Use static to analyze force like the weight of lifted object, wind pressure, and seismic load. Static help engineer design safe crane by determining the maximum load, required wire tension, and the proper crane setup. Last but not least, uniform rod suspended by a rope. A crane arm resembles a uniform rod held by a cable at one end. Static help engineer analyze force acting on the arm and cable, ensuring safe crane design. This includes calculating the maximum load, optimal arm angle, and cable tension. The ladder scenario highlights the importance of ensuring stability to prevent it from sliding or falling when leaning against the wall. This is crucial in the activity like construction, maintenance, and firefighting, where safety is a priority. Key factors affecting ladder stability include the angle of insulation, friction at the base, the weight of the ladder and the person, the height of the contact with the wall, and how forces are distributed. A person moves on the ladder, the center of gravity shift, influencing stability. For equilibrium, the forces such as a normal force from the ground, friction preventing slipping, and the wheel's friction force must balance additional the total moment about any point. Usually the base must equal 0 to prevent rotation. The challenge is determining how high a person can climb before the ladder slip. Understanding this principle helps engineers and safety experts designing better equipment and establish safety ladder use practice, reducing accident and improving workplace safety.
For mathematical modeling, there are four forces acting on the ladder, which is first is normal reaction force, static friction force, weight, wall reaction force. And there are two assumptions, which is frictionless wall, pivot point at the ground contact. For equilibrium condition, net force is horizontal and vertical, and the net torque about the pivot point. For equilibrium condition, horizontal force equal to friction force minus force equal to 0, and vertical force equal to normal force minus by weight equal to 0. For torque, tau times weight equal to negative L over 2 weight cos beta, and tau force equal to LF sin beta. Total torque equal to negative L over 2 weight cos beta plus LF sin beta equal to 0. So this is the free body diagram for the ladder resting against a frictionless wall. The numerical data given is weight equal to 441.45 Newton, ladder length is 6 meter, and angle beta is 55 degree. And the calculated result for horizontal force is 166.3 Newton, normal reaction force is 441.45 Newton, static friction force is 166.3 Newton, and the coefficient of friction is 0.377.
Assalamualaikum. Today I will present about discussion. A discussion about a ladder leaning against a wall is a common topic in physics, especially in the context of static equilibrium and friction. There are different ways to approach this problem depending on assumption and variable involved. The condition of the ladder to be in equilibrium are the net force acting on the ladder must be 0. This means that the sum of the force in horizontal and vertical direction must be 0. For example, the normal force from the wall must balance the horizontal component of the weight of the ladder, and the normal force from the floor must balance the vertical component of the weight of the ladder and the person on it. The position and weight of a person on a ladder significantly affect its stability by altering the system center of mass and influencing the top, normal force, and frictional force at play. A higher position increases torque, raising a risk of toppling, while a lower position reduces torque but can decrease wall friction, causing sliding. Factors such as ladder height, angles, and surface friction coefficient also play a role. To maintain stability, individuals should ascend and descend slowly. Face the ladder, maintain 3 points of contact, distribute weight evenly, and avoid overacting or carrying heavy items. They should stop at least 3 rungs from the top of a straight ladder and not exceed its safe walking load. To summarize, the issue of a ladder leaning against a wall exemplifies the use of fundamental principles in physics, including equilibrium, force, and moment. It also demonstrates how various factors can influence the stability and safety of both the ladder and the individual using it. The issue can be addressed through vector analysis, trigonometry, and algebra to determine the unknown variables like the normal and frictional force, direction force, and the least angle of incline. The issue can likewise be broadened to include more intricate scenarios like a ladder leaning against a curved wall, a hinge ladder, and a ladder equipped with spring. The issue of a ladder leaning against a wall serves a valuable illustration of how physics aids in comprehending and addressing practical problems. Recommendation: a ladder leaning a wall is a traditional physics dilemma that encompasses ideas like force, torque, friction, and equilibrium. The resolution and suggestion for this issue rely on specific factors provided, including the ladder's length and weight, the angles of friction coefficient between the ladder and the wall of flow, as well as the location and height of an individual on the ladder. One potential inference is that the ladder will stay in position as long as both the net force and the net torque on it are zero. This indicates that the normal and frictional force at the contact point must counterbalance and weight of both the ladder and the individual. Another potential conclusion is that there exists a minimum angle that the ladder can make with the ground to avoiding slipping down. This angle relies on the friction coefficient between the ladder and the ground, as well as the placement of the ladder centers of mass and that of the person. That's all from me. Thank you.